Okay, this is example 3 in section 3.3. It's another max-min word problem. This one deals with area. So it says a gardener uses 60 meters of bordering to form a rectangular garden. One side of the garden touches a wall and doesn't need any bordering. Algebraically determine the quadratic function that models the area of the garden and use it to determine the dimensions of the garden which result in having the greatest area, and state the domain and range of the variables. Okay, so what we have over here is a little diagram of this problem. So we need 3 sides of a rectangle, or we need to basically fence off 3 sides of a rectangle. So what information is the problem giving us? First, we know that the perimeter of the fencing or bordering is going to add up to be 60, because that's how much of it we have to use. And we know that that is also equal to all those sides added up. So it's the width plus the length plus the other width, or we can say twice the width plus the length. So we can use all that information to say 60 is equal to twice w plus the length, and we can solve this for one of the 2 variables, because we're gonna need that later. So let's solve this for length, just because it's easier, and get that the length is equal to 60 minus 2w, or 2 times the width. So why did I do that? Well, we know that we want a quadratic formula to maximize area, which in the area of this rectangle is going to be equal to length times the width. In order to make a quadratic out of that, we're going to need to sub in something for L or W and hope we end up with a quadratic, which hopefully you can see that when I solved for L and perimeter, that's where we're going. So we can model our area as just in terms of W by subbing in this other equation for length that we got from the perimeter. So area is equal to that. And we'll say that that's 60w minus 2w squared. Or if you want to rewrite that so that the squared term is first, you can. So we know we're looking for a maximum, and which that agrees with this equation, because this is going to be a quadratic with that shape because our a is negative. So we do have a maximum that occurs at the vertex. So we can find our x-coordinate of the vertex, which for this formula is going to be our width. So our width at the maximum will be equal to minus b over 2a, which is negative 60 divided by 2 times negative 2, which is negative 60 over 4, which is 15. So at maximum area, our width is 15 meters. And we can sub that back into our equation for length. So at w equals 15, we have length is equal to 60 minus 2w. So that's minus 2 times 15. So that's 60 minus 30 is 30. So what we have here is, this rectangle, and we've made a 15 by 30 rectangle like that. Let's find out what the actual maximum area is by just plugging in our w into our quadratic here. Why bother with doing that when we can just say, well, it's going to be length times the width, which is equal to 30 times 15. It's 450 meters. You could also have used the quadratic over here and said a is equal to minus 215 squared plus 60 times 15. Gives you the same answer. Squared, meter squared, with a little more work to get there. So we're almost done. Let's talk about the domain and the range. So hopefully you can see now that because we have 60 meters of fencing to use, that, well, first of all, when we're talking about domain and range, our minimum values are always going to be 0, right? We can't have negative distance of fencing. That doesn't make any sense. So we know that the domain for our width is at least going to be this much. Just can't go negative. But what's the maximum value? Well, if we have 60 meters of fencing to use, if our length was 0, we at most could have, we need a rectangle, so either side of the rectangle could be at the most 30, right? So if, because we need to split up 60 meters total and we have 2 widths, so you really just look back to our equation here. If length was 0, our width would be 30. So there's our domain. And of course, we can have real numbers here. So W belongs to the real numbers. And the range, same kind of thought process. If you had 0 width, you can't have negative length, so we'll start there. And if our width was 0, you should see that all of the bordering would be used in the length, which, of course, this doesn't really make any sense if you're trying to make a fence, but purely just thinking domain and range, if we had no width, we'd have at most 60 meters of length. So there's our range for this problem, or our range on the length. If we want to talk about range really on our, I guess we should talk about the range on our area, because that's what we wrote our equation for. The range on area would be, of course, if either the length or the width was 0, we'd have 0 area. So I'm going to say A here, and we just calculated a maximum of 450. And we can have everything in between. So again, you could do this 2 ways. You could have modeled it in width like we did, or we could have written an equation in terms of length. So maybe what I should say instead of range there for length, we'll call both domain, depending on the equation that you wrote, and the range will always be in terms of area, because that is what we were modeling in the first place. So there you have it.